Okay, morning guys. Can one of you just unmute yourself and just tell me that you can hear me all right? Oh, you're all
absolutely clear as a day, sir.
Okay, Harry.
Hello.
Okay, so we got 18 people here. I was expecting more than that, so I'm just going to give them another minute or so to get here. If you haven't yet said hello on the chat console, could you do that, please, just as a register? And then on Classroom, I sent you a PowerPoint, which I'm going to go through now, which you can watch on my screen, but later on, just in case you need it, it is there on Classroom if you want to look back on it. So you might want to download that while we're waiting, and then there are going to be some questions that you need to do later in the lesson. And again, I've put the PDF for that on Classroom as well. So just have a look at that while we're waiting. We're going to start in 2 minutes. Just give people a chance to get here. Morning, chat. Can you just write hello on the chat thing? Just for a register. Reese, I think you've already said hello a number of times. Okay, I'm going to turn the chat off now, so you won't be able to type on it. So if you need to say anything or interrupt me, you're going to have to just unmute. Thank you, Jack. Okay, so let me share my screen. Presence window. Okay, so I think how this is working, is that you should have my video feed and you should have my PowerPoint both showing on your screen at the same time. The PowerPoint should be big and the video should be small, but if you click between the two, you can make it swap the other way around. So you can make the video big and the PowerPoint small just by clicking on the video and then click on the PowerPoint to make the PowerPoint big as well. So I'm really just standing in front of the camera just to say hello. Well done for making it to the Google Meet. I'm sorry if this is starting to feel a bit like lockdown again. If it's any consolation, you're sitting in the nice comfort of your home with chocolate on tap, perhaps, whereas I'm standing in D1 in an empty room talking to myself, feeling a bit stupid. So really, I'm just saying hello. I'm going to move to the PowerPoint, and there won't be much use for the board today. And what we're going to do is have a little look at finishing off your table in your books. So you've got a uses column in that big A4 table that we've been making, and you haven't finished that last column off yet. So you just need to get out a pen and get out your book and just be ready to write some stuff in the uses column. Okay, so I'm going to switch to the PowerPoint now. Okay, so on the screen in front of you, you should be able to see that there's a picture of a smoke detector. And there's loads and loads of uses of alpha particles, but the exam board has just picked out one of them that they want you to focus on. So you've probably all got a smoke detector screwed to the ceiling in your house. You might have one downstairs, one upstairs. So you might have more than one. And it might come as a small surprise to you that actually inside the smoke detector is a little piece of radioactive substance. It's very, very small, a really, really tiny little flake of radioactive stuff. If you were to open it up and have a look at it, I don't know, it's about, I don't know, the size of your pen nib that you're writing with. It's really very small. So you obviously have to go inside your smoke detector sometimes to change the batteries, maybe. So if you were to ever open up the inside of your smoke detector, you would see that it looks a little bit like that picture on the right. And you can see that the battery is at the bottom, and that's the bit that you need to take out if you need to. And then there's a circuit board, which does all the clever stuff. Any of you that do electronics might know a bit more about that than I do. And then the big white thing on the right-hand side is a buzzer. So when you press the test symbol or when you burn the toast, it's that thing, that buzzer, that makes the really big screaming sounds, that piercing sounds to make your head hurt. And then also inside the smoke detector is this little kind of cylinder, which is actually a cage. There's holes in it. I don't know, you can't quite see them on the side of the black thing there. It's not very clear, is it? But it's a cage. If you do have a smoke detector in your house that is mains operated, if it's wired into the mains, you can't get inside your smoke detector. But if you've got a battery powered smoke detector, the flap just flaps down and you can have a look inside it. As long as you don't go poking around and touching things inside your smoke detector, I don't think there's a problem with you opening the flap to have a look inside it later on today. Like I say, you have to open the flap to change the battery once a year anyway. So by all means, have a look at your own, and then you can have a closer look at the cage. Like I say, though, if it's wired into the mains and it doesn't have a battery, you probably can't take the lid off it, and it's probably not a good idea to start poking around if it's attached to the mains. But there'll be a word printed on it that says "open here" if it's battery powered. So you'll be able to do that if you see that "open here" words. Okay, so what's inside the cage? Well, it's a couple of centimeters across, because alpha particles, which are coming out of the radioactive material inside the cage, they can't travel more than a couple of centimeters, remember. So you have got this cage around them just to stop your fingers actually accidentally going anywhere near the radioactive material when you do open it up to change the batteries. But all of the radiation is entirely inside that cage. It can't travel more than a couple of centimeters. It can't get out of the cage. Okay, so what's the point? Why is it there? So let's have a little look at the next slide. This is kind of a picture of what's going on inside the smoke detector. So what we've got is there's a circuit that's pushing an electric current round and round and round and round. And the circuit board is just paying attention to whether or not a current is flowing. And as long as a current goes round and round and round that circuit, the beeper doesn't beep and everything's happy. But how's it working? Well, there's a gap in the wire. So there shouldn't be any electricity flowing ever, because electricity can't flow across gaps. But if you remember about alpha particles, it is really, really, really ionizing. If you remember, that word means that it's capable of ripping electrons off atoms. And as we will study later on, electrons are the basis of electricity. And so what the alpha particles are doing in this gap are filling this gap with electrons. They're ripping them off the air that's in this gap. And then the electric circuit is going, oh, look, there are some electrons after all. And the electricity flows across the gap using the electrons. Now, we will do a whole topic about electricity later, and we'll find out what electricity's got to do with electrons. But for now, all you need to know is that as long as the alpha particles can get into this gap, the current goes round and round and round and round, and the circuit board is happy, and the alarm doesn't get sounded. But if there is smoke in the house, then the smoke fills up the room, then the smoke goes into these little holes on the case of the smoke detector, and then they get inside the smoke detector, and then they get inside the cage where the radioactive material is. And then once it's inside the cage, it gets inside the gap in the circuit, and then the smoke stops the alpha particles from getting to the gap. Remember, alpha particles basically can't travel through anything. They can't get through a couple of centimeters of air, they can't get through a piece of paper, and they certainly can't get through a little bit of smoke. And so what happens is, as soon as the smoke fills this gap, the alpha particles can't get there anymore, which means they can't make electrons appear in this gap, which means the current can't flow, and the circuit board notices and it says, hey, where's my current gone? There must be smoke inside the smoke detector, and so it sets off the alarm. In actual fact, it's not really a smoke detector. It's just stuff inside my smoke detector. So you might find that if you accidentally leave your kettle boiling near to your smoke detector, the steam from your kettle can set off the smoke detector. If you ever have any DIY or anything going on in your house and there's a load of dust in your house, you know, if you're sanding down some woodwork or something, if you get a load of dust in the air, even the dust can set off a smoke detector. So a smoke detector isn't really a smoke detector, it's a stuff in the air detector. But obviously smoke is the stuff we're interested in because that's the danger. So you need to be able to tell an examiner that if they say to you, what do we use alpha particles for? You need to be able to say, we use them in smoke detectors. That'll get you 1 mark, but the question might be a 2 or 3 mark question, in which case they might ask you, how does it work? And the bit you need to get across is that the alpha particles ionize the air, but the smoke stops that from happening. So in your box, in your table, if you could just write in the uses column for alpha particles, if you could write down that we use them in smoke detectors, and just a couple of sentences or a sentence just to say, we're used in smoke detectors to ionize air, but the smoke stops this from happening.
I wasn't in when we did the table.
Okay, so maybe after this lesson, if you just get in contact with somebody else in the class and ask them to take a picture of their table and zap it over to you and you can copy it out.
Yeah, all right.
Okay, so I'm just gonna just shut up for a minute and let you write in that box and then we'll move on to beta. So I'll give you 1 minute.
What are we writing?
So in the, shall I write it on the board? I'll write it on the board. Hang on a minute.
Sir, can you write it a bit bigger because it's like really small?
Yeah, will do. Is that big enough? I bet you're on your phone, aren't you? I bet it's tiny on your phone screen. Remember, if the board is looking very, very small, you can flick between the board and the PowerPoint by just tapping or clicking on the video, and that will make the video picture big and the PowerPoint will go small, and then you can flick back by clicking on the PowerPoint. Okay, everybody ready to move on? So let's have a little look at what we use beta for. So before I show you the screen, see if you can guess this one. So until a couple of years ago, something like the 7th richest person in the UK owned a manufacturing business. They made something. And the thing that they made, they exported all across the world, to every country of the world. And for about a decade, they were the only company in the world that could do this because they were so good at it. And they were so good at making something that nobody else could make as perfectly as they could. And because they could make it so perfectly, the people who ran the company, they just made more money than they knew what to do with. And they were like I say, 7th on the UK rich list for years and years and years, until the rest of the world caught up. And they did it by using beta particles. Can you think about anything that you might manufacture, anything that would be made in a factory in bulk that the whole world wants, and we use beta particles to check that it's perfect after it's been made. And your clue here is that beta particles can kind of get through stuff and kind of get stopped by stuff. They partially go through, partially don't. So have a little think. I'll ask for answers in 30 seconds. Okay, guesses. Anybody want to take a guess? What got manufactured that the whole world wants that that's hard to get perfect? Any ideas? Just unmute yourself and shout it out.
Or was it a smoke detector? Because like, was it like how you said that they can separate it from sawdust and then it would go off, so it would only be smoke?
Okay, that's not right, because again, that would be using the alpha particles rather than the beta particles. So we're looking at beta now. Can kind of get through stuff, kind of can't. Any other ideas?
What's the cancer treatment called, sir?
Oh, we're getting onto that. You've just skipped ahead. That one's going to be gamma rays. So you've just answered the next question. So yeah, we use gamma rays for cancer treatments. We'll come to that in a sec. Good one. Still on beta though. Any ideas for beta?
Could it be a battery?
No, again, good guess, but no. This is something that's quite thin, actually, that we need to shine the beta particles through. Can you think of anything that's very thin that gets manufactured a lot?
Solar panels.
Thinner than that, and simpler than that. Might be really very tricky right now. Pardon? Did you say?
A metal.
Yeah, metals. So there's two answers to the question, and that's one of them. The person who was actually 7th on the rich list manufactured sheet metal. So that was metal that was very, very, very thin, but in really big panels. And the car industries all over the world used to use sheet metal to build the bodywork of cars out of. And the factory in Britain at the time, it was the only factory in the world that could guarantee that the metal that they would make for the car manufacturers was going to be something like 1/3 of a millimeter thick. And no other company could guarantee that it would be exactly 1/3 of a millimeter thick, all the way across the whole surface of the metal. No thick bits, no thin bits, no lumpy bits, no bent bits. They could make perfect sheets of metal that were exactly 1/3 of a millimeter thick. And given that this metal was coming off the production line, really super hot and really super fast, and it was so thin that you couldn't really measure it with a ruler, they had to work out a way of working out if the metal really was the right thickness or not. And they used beta particles for that. And we'll come to how they did it in a second. What's the other thing that you're actually touching right now, not your phone, that is very, very, very thin, and you've got loads of it, and all of it is the same thickness or the same thinness?
Air.
Not air, something manufactured.
Skin.
Pardon?
Skin.
No. Something we make, something you're holding or leaning on right now.
Plastic.
No.
Table.
Really thin.
Paper.
You're writing on it.
Paper.
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 Paper, yeah. So this is the most
Ah.
boring thing to ever think about in the world. But the book that you're holding in your hand right now, just flick through it and just feel that every single page is exactly the same thickness. Nobody claimed this is an exciting thing, but it is a get you rich quick thing. If you can make paper that is that thin and is all perfectly the same, no lumpy bits, no thick bits, no thin bits, then you've got a manufacturing business waiting for you right there. So let's have a little look how it works. So metal or paper is the same principle of the same one. So if you were just on your camera, just flick back to the PowerPoint. So this is the basic idea in a factory, that we're making sheets of either paper or metal. And in order to get it the right thickness, it goes through rollers. So the rollers on the right-hand side, they squeeze the metal or the paper pulp. Paper's made from like mashed up tree. It's like a mulch, like papier-mâché, but not quite that wet. And you send it through a pair of rollers, or molten metal. You get it really, really hot so the rollers can squash it. And it goes through a pair of rollers. The rollers on the left are just to guide it, but the rollers on the right are what are squishing it and getting it to the right thickness. But that roller might be squeezing metal at like 2 or 3 meters per second. It's zooming by really fast. And we can't keep stopping the rollers to measure the metal or the paper to make sure it's the right thickness. And even if we did, how would you even measure a piece of paper anyway? It is so super thin. It's not like you can use a ruler to do that. So what they do instead is they take some radioactive material and they just put it above the metal or the paper, and the beta particles come firing out of the radioactive material, and some of them make it through to the other side of the piece of paper or the piece of metal where they're detected. And what happens then is that if the paper is too thick, not very many beta particles will make it through to the detector. And the detector will notice that there aren't very many particles, and it'll tell the computer to move the rollers a little bit closer together because the paper or the metal's too thick and not enough beta particles getting through. So move the rollers together to squash it a little bit more. Or maybe one day the detector manages to detect too many beta particles. There's too much getting through. That means that the metal or the paper is getting really too thin. So again, the detector would tell the computer to move the rollers apart because they're squashing it too much. So move apart a little bit to allow the paper or the metal to get a little bit thicker again. Okay, so what do you need to write down in your table? Pretty much, you just need to write down the title from this slide. Paper and metal manufacturing use beta particles for thickness monitoring. That's all you really need to summarize in your table. So just copy down the title from this slide. Paper and metal manufacturing use beta particles for thickness monitoring. I'll give you a minute to do that. Okay. Again, there are other uses for beta particles, but that's the main one. And if you're ever asked in a test or an exam, what do we use beta particles for? You pull out thickness monitoring in manufacturing, like paper or metal. Any questions? Okay, let's have a little look at gamma then. So we've already been given one of the answers for gamma rays. Someone said it's used in cancer treatments, and that's completely correct. And that's because gamma rays can get through stuff. Alpha can't get through anything. If you tried to shine alpha particles onto a person, it'd just hit the top layer of skin. And icky as it is to think about, your top layer of skin is actually mostly dead skin cells anyway. If you want a truly icky thought, take a dustpan and brush around a surface in your house, and 90% of the dust that you sweep up, 90% of the dust are your own dead skin cells that flake off every single day. Every time you wander around your house, bits of the top layer of skin cells just flakes off and goes and settles all over your house. So that's a nice thought, isn't it? So alpha particles can't even get through that. So we couldn't use alpha particles for any kind of human treatment because it can't get inside you. Beta particles kind of get inside you, but only a little bit. They wouldn't go very far inside a person. Gamma rays, on the other hand, can go straight through you, and most of them come out the other side, but some of them will still destroy your cells, like we spoke about in class the other day. Now, what you just want to do is target the right cells. So we spoke about the dangers of radiation. It's possible for alpha, beta, and gamma to cause a cancerous cell to develop. But once a cancerous cell has developed, you can use gamma rays to destroy them. So I guess good and bad at the same time. So what you can do with a gamma ray is really target it really precisely on exactly the place in the human body that you want to destroy. So you don't accidentally destroy the wrong bits of the human body. You can focus it really, really accurately and zap the cancerous tumor to try and destroy those cancer cells. So that's called radiotherapy. And that's one of the pictures on this next slide. So there you go, that's the top picture. And you can see that there's a patient who's been, that metal circle around their head, that's to keep their head in place. And you can see all those beams, those are gamma rays, all shining through tiny little holes in that metal cylinder around the patient's head. And that's to make sure that the gamma rays only go where we want them to go. And there's loads of beams, because if we were to shine one really powerful beam, it would destroy healthy tissue. Whereas if we fire lots of low power beams, then each beam on its own doesn't really do anything, but where all of the beams meet, there's enough power there from all of the beams combined to destroy the cancer cells. So that's what we use gamma rays for. We use them to destroy tumor cells. So if you want to write that in your uses box for gamma rays, destroy tumor cells, or you could write cancer treatment. That would work as well.
Does chemotherapy use this as well?
Say that again?
Does chemotherapy use this?
So chemotherapy, the CH at the beginning of chemotherapy, that's the chemicals. So chemotherapy isn't radiation, it's a chemical attack. But quite often we'll use the chemicals and the gamma rays together for a kind of two-pronged attack on the cancer cells. So you might have some radiotherapy and then follow up with some chemotherapy afterwards, or the other way around. But yeah, they're different things. Chemotherapy and radiotherapy are different things. This is the radiotherapy with the gamma rays. However, there are 2 more pictures on that slide. So what do you think is the reason I put an apple and some scalpels on this slide? What do you think we're doing to them?
Is it because the gamma rays can get into apples and make your food like radioactive?
Okay, so remember, radiation can't make stuff radioactive. So it's not like, the opening sequence on The Simpsons or anything like that. Radiation doesn't make stuff glow in the dark. It doesn't make fish have 3 eyes. It doesn't make people grow another head or anything like that. Radiation just kills cells. Radiation is just bad for humans. So, and apples, if it was still on the tree. But this apple has been picked, and so it's not attached to a tree anymore. It's not getting any nutrients. It's not getting to grow. So for all intents and purposes, that's a dead apple. So shining the gamma rays on the apple doesn't actually do anything at all to the apple. It's still exactly the same apple in exactly the same shape it was before we shine gamma rays on it, which begs the question, what's the point? If it doesn't do anything to the apple, why do we shine gamma rays on the apple?
Is it for people to eat and then maybe it doesn't?
Okay, so you could eat the apple completely fine if you went to the apple tree and picked it off the apple tree without it being shone with gamma rays. So it's not about making it more edible or anything like that. It's more to do with the fact that you personally haven't been to an orchard and picked the apple off the apple tree. You've probably got an apple that came from a supermarket. So what might that mean for the apple? Okay, what might happen if you go to the orchard is that you could pick the apple and you would eat it like there and then, or that afternoon when you got home, or tomorrow. But if you go to the supermarket to buy yourself an apple, that apple might have been picked off the tree maybe a month ago. What might have happened to the apple in that month? Or what would you expect to happen to an apple in a month? If you left an apple in a fruit bowl for a month, what would you expect to happen to it?
It would rot.
It'd rot. And yet the apples
Let's go, baby.
Say again? Yeah. The apple doesn't rot. It's picked off the tree, and then it might take at least a week to get on the lorry, travel across the country, get put on a shelf in a supermarket. Sometimes the apples are stored in like a fridge for a while because the supermarket might have too many apples, and they can't put them all out on the shelves at the same time. So when you munch into an apple, it might have been a week, 2, 3 weeks since it was picked off a tree, and yet there it is, not rotting. So what do you think the gamma rays did to it to stop it from rotting?
Preserve it.
But how? What makes it rot anyway?
Like exposure to like air and stuff.
It is exposure to something, not air, something in the air. Apples don't rot on their own. Nothing rots on its own. Something causes it to rot. What does rot mean? Think about biology. So food only rots because it's got bacteria on it. Bacteria that causes stuff to rot. If you could have a spotlessly clean world that didn't have any bacteria in it, nothing would rot, ever. So bacteria does serve a really good purpose in the world. It breaks things down so that the chemicals can go back into circulation. So, when apples fall off the tree, you want the apple to rot so that the nutrients go back into the soil for the next tree to use. But you don't want your apple to rot because you want to be able to eat it. So what we need to do is get rid of the bacteria off the apple. And there's bacteria in the air all the time landing on the apple. So what we really want to do is just make this apple really, really clean. But we don't really want to take a scrubbing brush and some disinfectant to our apples because who wants to eat an apple that's been scrubbed with disinfectant? So we just need a really quick, simple way to kill the bacteria on the fruit. And it's not just apples. Pretty much any fruit or vegetable that you've ever eaten, unless you went and picked it yourself, if it came from a supermarket, it's probably had gamma rays shone on it to kill the bacteria. And that's why stuff on the supermarket shelves lasts for days, maybe even a week, instead of just one day. It would be rotting really quick if we didn't get rid of the bacteria off it. So nearly all of the fruit and vegetables you've ever eaten has had gamma rays shone on it to kill the bacteria. But just to be clear, shining gamma rays onto stuff only destroys living cells. So the bacteria are living cells and it destroys those, but the apple picked from the tree, those are no longer living cells. There's no chemical reactions going on inside the apple anymore. So it doesn't do anything to the apple. And in particular, it doesn't make the apple radioactive. So carry on eating all your fruit and veg because the gamma rays don't do anything to it at all, apart from kill the bacteria to stop it rotting. So you
Don't they put like wax on the apples?
They do actually. That's more to make it shiny so that it looks nice to eat. But I guess it probably does create a barrier to stop more bacteria getting in. Yeah, it's a good point. Kills bacteria. And then the scalpels are a bit like an apple in terms of why. So what do you think it does to the scalpels?
Right, disinfects them.
Yep, same thing. So your skin is your barrier to bacteria. That's why when you cut your finger or something, you need to make sure that you wash it under a tap to make sure that no bacteria from whatever you cut yourself on has got under your skin, got through your skin barrier. So if you're going to go in for surgery and somebody is going to deliberately cut into your skin, well, that's going to leave a hole ready for bacteria to get into your skin. And what you certainly don't want is for the knife they cut you with, the scalpel, you don't want that to have bacteria on it, because when the surgeon cuts through your skin, it's going to carry that bacteria deep inside your cells, and that's going to create blood poisoning eventually. In fact, the number one cause of death when surgery was first getting going decades ago was that people would die of blood poisoning after the surgery. So the surgery would go really, really well, and the surgeon would be really pleased with themselves, having done a really good job, and then their patient would die. And believe it or not, it took about 20 years for people to work out that washing your hands and washing the scalpel and washing the patient before you did the surgery really saved lives, because it reduced the amount of bacteria going into the patient. But even washing isn't good enough. You need that scalpel to not just be pretty clean, you need it to be perfectly clean. And a little bit of fairy liquid and a sponge isn't quite good enough. It also blunts the scalpel over time if you keep washing it with water. So what we use instead is the gamma rays, because they destroy every last piece of bacteria on the scalpel before it goes cutting into the patient. Okay, I'll give you a minute to write that down, and then I'll tell you what's happening next. Okay, So we've now finished our table. You now know a little bit about the properties of alpha, beta, and gamma, things like what they are, whether they're positive or negative, whether they're a particle or a ray of energy, how far they can pass through objects, whether they can rip electrons off objects, the ionizing, whether they swerve when they go near to a magnet. You know about the dangers of these things, about whether they can destroy cells or maybe damage cells, which can lead to cancerous tumors. And you also now know some uses of these things. What we put them to work doing for us in our everyday lives, like with our fruit and veg and with our smoke detectors. If you can memorize that table, there won't be much in physics that I ask you to memorize over the 2 years, but that table, if you can memorize that table, it's just easy marks in a test or an exam to be able to recall some of that stuff. So do your best to try and remember what's in that table. Try and memorize it over the next few weeks or so. Keep glancing back in it. Every time you get your physics book out for the next couple of weeks, just glance back at that table and see if you can get it to stick in your head. Okay, there's 2 more words that I need you to learn the meanings of. So just put them on the screen. So I've used these words with you in class, some of them, but I just need you to know what they mean and to write down what they mean. So if you've been exposed to the alpha, the beta, or the gamma, the radiation, then we would say that you have been irradiated. So if I were to give you a lump of radioactive material and you just waved it near your hand so that the radiation came out and the radiation hit your hand, then you would say that your hand has been irradiated. On the other hand, if you were to open up the little packet of radioactive material so that you could see the material itself and you sprinkled the radioactive material onto your skin, then that's something completely different. You've now been contaminated by the radioactive material itself, not the radiation coming out of it, the actual material. And what that is so much worse because it's now on you and it's going to be continually irradiating you. You would hope that normally irradiation would just be a really momentary thing, that you momentarily meet a beta particle, it momentarily hits your skin, and then it's all done. But if you get contaminated with the radioactive material that's releasing the alpha particles or the beta particles or the gamma rays, then you're going to get continually irradiated because it's releasing radiation on you all the time. So if you've been contaminated, that can be so much worse, and you need to be able to shower to get the contaminated dust off your skin. Of course, if you've breathed it in so that it's in your lungs, then that's really, really very serious indeed. So luckily for you, there's very little radioactive material in your environment, and the chances of you breathing any of it in is almost non-existent. But if you were working with nuclear material as part of your job, if you were working in a nuclear power station, or if you were working making nuclear bombs or something like that, or even if you're in a factory making smoke detectors and they're manufacturing these little radioactive nuggets to go inside those cages, or if you're working in a hospital and you're dealing with the chemicals that would release the gamma radiation for that machine, then you'd have to be really careful to make sure that you didn't get contaminated with that. You wouldn't want to be irradiated either, but you certainly wouldn't want to be contaminated. Okay, so that's the 2 words for the column, for the paragraph headings: irradiation and contamination. And then there's another couple of words in bold on that screen. So you know when you go to the doctors and they give you some antibiotics, and they say the dose is 1 tablet a day. That means how much did you get? I want you to get 1 tablet a day. It's your dose, how much you got into your body in one go. So we use the same word for how much you've been irradiated. If you have been exposed to alpha, beta, or gamma radiation, the question becomes, how much alpha, beta, or gamma radiation have you been exposed to? What was your dose? And we measure the dose of chemicals in grams. So you might say, paracetamol. I've got a headache, take 500 grams of paracetamol, 500 milligrams of paracetamol twice a day or something like that. That would be your dose in grams because it's a chemical and you can weigh it out. But with alpha, beta, and gamma, you can't really weigh it out. So what we say instead, we use a unit called the sievert. Now, you don't need to remember that unit. I've just put it there because you'll see it in revision guides, and I don't want you to see it and get confused as to what it was. But you don't need to remember that it's called a sievert. What you just need to remember, though, is that you live on a planet that's only a little bit radioactive, which means if you wander around this planet for an entire year, you'll get a dose of, on average, 2.7 thousandths of a sievert, 2.7 millisieverts. That is just nothing at all. It's basically zero. It's, 2.7 millisieverts, like 0.00123227. It's just no dose at all, really. Pretty much zero. Sometimes examiners try to catch you out and they say, oh, well, if you live in Macclesfield, that's how much you'll get in a year. But if you go live in Cornwall, you'll get that much. And the question will be, is it more dangerous to live in Cornwall? And you have to say, well, technically, yeah, but it's not really dangerous to live in either place because both places are practically zero. So your dose is very, very small naturally. However, if you were to work in the nuclear industry and your job was to work in a nuclear power station, then that number is going to be bigger because you're around radiation all the time and you get irradiated just turning up to work. So we start then asking, well, what's a safe dose and what's an unsafe dose? So 2.7 would be considered to be normal. Once you start pushing like 10 or 15, that's starting to be a level of concern. And certainly if it got any higher as like 50, then you'd be seriously worried. And usually at 100, people would die. So yeah, 2.7 is really low, but we quite like it being really low, and we wouldn't want to take it any higher, really. So could you please copy down into your book what's on that slide? So I'm going to give you 4 minutes to do that, because that's quite a lot of words. So 4 minutes, and then I'll come back to you. Okay, you got 1 more minute for that. So if you're still writing, keep writing. However, while you're writing, if you could just listen for your name, Izzy Collingwood, Reese, Kayla, Carly, Harley, Isla, Alkana, Jack, and Zach, all of you have not handed in the homework that was due last night. So given you're at home and you've got time on your hands, I am going to give you an extension until the end of today to get the homework done from Classroom. It is just a 10-question multiple choice thing. It's on Classroom.
I wasn't in when it was set.
Okay, add it onto this week's homework then. So it's a 10-question multiple choice test. It'll only take you a couple of minutes.
Okay.
It's on Classroom. Okay, time's up. You have got access to the PowerPoint. So if you have not quite finished doing it, then you can look yourself. What I'm just going to do is each of our 2 lessons this week, I'm just going to set you a short 15-minute homework. So I'll give you a little bit of homework today and a little bit of homework next lesson. And that's because you're at home basically, and you can manage your time and do things in whatever order you want. So I'm just going to ask you, if you wouldn't mind, to just do the following. Let me just share my screen again. Share. Okay, so on the same Google Classroom post from this morning is this PDF document. And it just talks about uses and dangers of alpha, beta, and gamma. And you've looked at some of this before, lots and lots of it. But just down here in the bottom right-hand corner, there are 3 or 4 questions about alpha, beta, and gamma. And you can see that they get darker in blue. So question 1's quite light, question 2's a little bit darker blue, and questions 3 and 4 are a deeper blue. That's showing you the questions getting more difficult. So what I'd really like is for absolutely everybody to do question 1. I think most of you could get question 2 done. And I think quite a few of you could have a go at questions 3 and 4. So I reckon that'll take you about 15 minutes, or rather, please spend 15 minutes on it and then just stop when you run out of time. Just have a go at doing those questions in your book. We've got another lesson later this week, and so I'll speak to you again then, and we'll do exactly the same format. So if you could just pick up your Google Classroom assignment that I'll post at 8:30 in the morning on the day of our next lesson, and again, just join the Google Meet at the start of our lesson. And we'll do this again. I'll walk you through another lesson and you can fill it in your book as you go along. Is that right? Any questions from today? Okay, I'm just going to very briefly turn the chat back on. If any of you arrived late and you haven't written hello on the chat, could you just write hello on the chat now before you leave? Otherwise, we are done for today. Well done, you. Have a good rest of your day. Bye-bye.
Cheers, sir. Thank you very much.
Yeah.